And now I'd just like to introduce our presenters and this session. So this session will present the basics of checking for steel girder stability during lifting. It will also cover temporary support of steel and concrete girders before diaphragms are installed. Topics will include lifting with spreader bars, multiple crane lifts, crane position and methods to provide girder stability. The session will present examples of actual girder lifts to demonstrate lifting procedures and present solutions to challenging projects. The presentation will include a summary of UDOT SDDM design requirements and the UDOT standard specifications. So we have Jeremy Price. Jeremy is a Utah native and has been with the department since June of '95. He worked in the department welding shop for 2 years, and since '97 he's worked in Central Materials as a structural steel and coatings inspector. Jeremy has over 30 years experience in structural steel fabrication. Jim Deschenes has a BS in civil engineering from the University of New Hampshire and an MS in civil engineering from the Missouri University of Science and Technology. He has over 20 years of experience as a bridge and structures engineering design consultant and currently is the Director of Alternative Delivery at Ralph L. Wadsworth Construction. Clark Olsen, as president and owner of Utah Pacific Bridge and Steel, has fabricated over 1,300 bridges during the past 42 years. Clark also provided transportation and erection installation oversight for most of these bridges. On a weekly basis, Clark advises designers throughout the country on economical steel bridge fabrication, constructability concerns, and project cost estimates. He served on the AISC Board of Directors and is a founding member of the National Steel Bridge Alliance. Mark Daniels. Mark has been a structures designer and structure design lead at UDOT for the last 8 years. Previously worked as an engineer for SME Steel Contractors and Core Brace. He enjoys spending time with his family, skiing, and biking. And we have Chad Anderson, who is RLW's crane superintendent with over 15 years experience erecting and de-erecting concrete and steel bridge girders. He started his career as an iron worker and is RLW's go-to resource in developing crane plans and erection sequences. Chad was the operator for most of the slides in this presentation. So I'd like you to welcome our presenters today, and please give them your full attention.
Thanks. I have a number of slides to get through today, and I'm going to go through them as quick as I can. It'll take about 45 minutes, I hope. And so if we can hold all our questions till the end, it'll help me out a lot. If you ask me a question during my presentation, you'll get me all flustered, and I'll go off on some tangent, never get back on track. So this is the girder stability during erection temporary bracing seminar. This is going to be somewhat academic as I go through this. We have some objectives for today. Become familiar with the key factors that affect girder stability. Identify situations where stability may be a problem. Understand the temporary support methods that are used practically out in the field. And understand UDOT requirements. As we go through this, my slide presentation, and if you download this or watch it online, everything that's in the slides that's in blue comes right out of the UDOT specifications or the SDDM. So that's just easy to pick up on as you go through this. The background of maybe why we're giving this presentation, I'll start with the last thing. Everyone has heard about last year at Florida International University. They had a bridge collapse. It was under construction at the time, and they opened traffic underneath it, and they were working on it. And it fell, and it was a pretty big disaster. And that was a completely different structure than what we're going to talk about today, but it just kind of underscores the fact that you do have to consider the condition of your bridge if you're going to open it to traffic before it's complete with construction. So that was kind of one of the things that made me come up with this presentation. Most of the bridges we build in Utah are steel or concrete girders. They're straight. The spans are relatively short. If you've designed for all of your regular dead and live loads and in particular deflection, your girder proportions are going to be such that they're stable during erection. But that's also kind of the danger part, because the engineers can start not paying attention to those types of things. If you just assume that all your girders are stable and you start going out there, either erecting them or even during design, just not even checking that, I think we'll start to see more problems. There are also a couple of factors I'll go through later that are probably making girder stability a little bit more of an issue, and Clark's got some stuff he'll talk about as well. Maybe some of you in here remember in 2004 there was a steel girder that collapsed in Colorado. It was erected, it wasn't stable, it wasn't braced properly, it held up for a while, they opened traffic underneath it, then in the morning when the sun came out and the girder heated up, some things happened, and the girder actually fell over, rolled over, and then bent about the weak axis down into traffic and actually hit a car as it was going under the bridge. And really, if they just paid attention to the things we'll go through today, that shouldn't have happened, and it should never happen here in Utah. It's easily preventable. It's preventable from the designer all the way through the erector. A little bit of background on the UDOT specifications, and this is in regards to maybe the FIU situation. This is what it says in the specs. Well, the top part is the concrete, and the lower part's the steel. The concrete's a little more explicit. It says you won't open traffic underneath the partially erected bridge until it's either been signed off on or the plans clearly show that when you can open it to traffic, and those plans have to be stamped and sealed by a professional engineer in the state. And the steel specification is not quite as explicit. It says the same thing. If you read other parts of the specification, it clearly states that your erection engineer and your erection plans, that they need to be stamped by a professional engineer. And this presentation will kind of go through some of the steps if you ever in this situation where you have to perform this duty, of how you can easily perform those calculations and check it with confidence. Again, the focus on this presentation is going to be typical UDOT bridges, which are concrete girders or steel girders. I'm not really going to get into curved steel girders, although that can be a particularly special problem. I also won't do trusses or tub girders or something like that. We'll just stick to what we typically have here in Utah. We'll cover concrete girders, plate girders, and then I'll go over this program. It's called UT Lift. It's a great little program. It was written by the University of Texas, and the guy who wrote it actually works for Michael Baker. So if anybody's got a question about the program, call Zach. He's back there. Just bug him, Zach Taylor. I don't have his number, but catch up with him. All right, and if anybody's going to leave early, because you're supposed to stay here for 35 minutes or you don't get credit, but if you want to go because you're bored, but you're interested in this subject, there is a document out there. This is FHWA, NHI document, and it's pretty much the definitive document. There's nothing that I'm going to say today that's not covered in this document, plus this document covers truss bridges, it covers some demolition, movable bridges, tub girders, it covers everything, and it's like 1,000 pages long. It touches on the UT Lift program that I'll talk about, but it's an excellent document, and if you're out there, if you're an engineer that does erection drawings, you should definitely download this. It's free. It's on the FHWA site, and keep it on your desk for reference. Again, most of the stuff we do in Utah is inherently stable, but sooner or later you will come across a situation where it isn't, and it's going to be handy to have this on your desk. Concrete girders. Concrete girders, they're inherently stable in terms of lateral torsional buckling. They're not going to just fall apart when you pick them up. They're not going to roll over. They're stable. They have thick webs. They have thick flanges. The lifting points are cast in place in the casting yard, and they're pretty much guaranteed when you lift from those lifting points, you're picking up at the center of gravity in the transverse direction, and they're equal spacing from the ends, so you're going to be picking it up with the center of gravity in the middle. You don't have to take my word for it. PCA says this, that NHI document I just talked about, it talks about concrete girders and just says they're stable. The Utah bulb tee or any bulb tee girder or AASHTO girder is just inherently stable. It's not just going to roll over. And here's an example. This is actually a girder we erected in Colorado. This is like 180 feet long. It's a bulb tee 72. It's not the Utah bulb tee, but it's a 72-inch bulb tee girder. And you can see two big cranes, really long span, but no need to brace it or have a whole crane or anything like that. I will say that the exception to concrete girders is something you have to watch out for is concrete girders, if they're on a small bearing pad, which typically doesn't happen in Utah, Most of our concrete girders are integral abutments and integral bents. So the bearing pad is a unreinforced elastomer or a cotton duct pad. It's the same width as the bottom flange of the girder. So the girder can't really roll over about the smaller bearing. But in some cases, if you do have an expansion joint, you may have a small bearing, and it could roll over. Concrete girders sometimes have sweep in them, which means they come out of the form and they have some horizontal offset. And that could be a problem, but it's unlikely that's a problem. If the sweep was so bad that it was a stability issue, it probably should never be delivered to the job site because it's going to be out of specification. I think there could be an issue if your bearing pad's not level, which could happen if you have a cross slope on your bridge and it hasn't been, the abutment seat hasn't been ground flat where you put your bearing pad, or there's just maybe they've ground it flat, but they didn't grind it flat in the right spot, and your bearing pad's not quite vertical. That could be an issue. So that's just one thing to be aware of on concrete girders when you're doing an erection plan. Here's a typical brace for a concrete girder. As you can see in the diagram, it's a single strut here that acts both in compression and tension. That's okay. We typically chain it on both sides, so it's tension, and you put a Hilti anchor or some other type of expansion bolt. You drill and drop it right into the abutment and connect an angle iron to it. That's a pretty stable system. You can't connect it directly to the rebar if it's an integral abutment bridge, and you typically have like number 8 bars coming out between the girders. If you have an effective way to clamp your chain or your strut to that rebar, that's fine too. That's a pretty common detail. The example shown here shows the small bearing. It shows it's a little pot bearing, and this is an example right out of the NHI book that I showed you. This actually failed during construction. I'm not sure what happened, if it got bumped into or there was some other factor, but because the bearing was so small compared to the bottom flange, the whole girder just kind of flopped over. But anyway, this is just one way to brace the girder. Again, UDOT specification, it does state that your concrete girders have to be braced or anchored down during construction. In Utah right now, the standard detail is the galvanized steel diaphragm between the girders, and that's effective bracing. So if you put your first girder up, you chain that down, you put up the second girder, and you just put in your steel diaphragms, the girders are stable. There's no need to put in any temporary bracing or anything like that, unless you are doing the cast-in-place diaphragms. That's not typical. I don't know if there's been a UDOT bridge that's come out with concrete diaphragms lately. At the airport, Chad and some of our other engineers has had to deal with concrete girder bracing because they've required the concrete diaphragms. They didn't want to use the steel diaphragms. And this is a problem that if you're an erection engineer, you maybe come across. The specification requires that you provide stamped calculations and engineering drawings for temporary bracing on a concrete girder. And sometimes this is hard to show because it's stable. The girder can't fall over. I mean, even if you do the wind load calculation for a 200 or 100 mile an hour wind and exposure C, and maybe 20 pounds per square foot is your load laterally on the girder, it can't blow the girder over. It's too heavy. Sometimes I'll come up with a scheme that, well, if girder 1 is set and they're swinging girder number 2 into place and something goes wrong and somebody gets a phone call or something and not paying attention, which doesn't happen because Chad's in the crane. You could technically, I guess you could hit the other girder, you could hit the top flange and maybe knock it over, but even then, just recently at the airport, we looked at that, it would take like a 20,000 pound force. So it's really not very realistic to expect that these concrete girders are going to fall over. But the specification still says provide calculations and a drawing. So I typically rely on some standard details. Texas, for one, has some standard details. You can download them from their website. What happened there? I think we lost power. So if you look at this detail, it really doesn't, if it ever comes up, it doesn't provide much. It's basically 4x4s and some number 3 bar that you weld to the existing rebar across the top of the girder. And the 4x4s just provide blocking between the tops and bottom flanges. I think if you really did a calculation, you'd find that it doesn't really provide much support, but it checks the box for temporary bracing anyway. Okay. So my next detail is the Idaho standard detail, and I was going to show that to you, but it doesn't mean a lot without seeing it. Idaho, and when the slide comes up, I'll show it to you, but Idaho, I don't know if they had an issue at some point a long time ago, but for as long as I can remember, Idaho's got this standard bracing detail for concrete girders that involves steel 4-inch HSS sections, which is steel tube sections, and it's got all these crazy details for bolts, and it's adjustable, and you bolt it into the girder, and it's good. But anyway, compared to the Texas detail, this can hold up the world. And most contractors up in Idaho, and I don't know if we still have these or not, but they have these braces. The good thing about them is you build them once, and you can use them. They're adjustable, so you can use them on every bridge forever, and they're going to last for a long time. The downside for this detail, if you ever want to use it, as you can see on the right-hand girder there, that they actually have bolts going through the web of the girder. If you were to put these braces towards the end of the girder, that's where you have some PT strand. So typically the fabricator will put those holes in there for you, so you'll miss the PT strand. But that is, to me, that's a drawback. If for some reason the fabricator didn't put those in and you wanted to use this brace detail and you had to drill holes in your girder, you wouldn't want to compromise your PT strand for the sake of putting in bracing that you don't really need. So that's my comment on Idaho's detail. But it will work. It'll definitely work. Here's an example in practice. This is at the airport just this summer where we've had multiple girders. These were on fairly small bearing pads. And so we did provide some let from bracing. This is similar to the detail that Texas uses, modified a little bit for the way we do it. It's hard to see in this photograph. The far right girder has been chained down to the abutment on both sides. And then there's just 4x4 bracing between the tops and bottom flanges of each one of these girders. And then we run a chain across the top to actually kind of put some tension in all the top flanges to hold them together. This is a pretty common detail that our guys like because it's fast to erect and it's fast to de-erect. It doesn't get in the way when you're doing your forms. So that's really all I need to say about concrete girders. Just remember they're stable. Just watch out for the bearings. Steel girders, this is much more critical. Steel girders are tall relative to their flange width. The flanges are very thin relative to the width of the flange. And they're susceptible to lateral torsional buckling, just like any other girder. If you remember if you took steel design, if you're an engineer, you remember lateral torsional buckling actually reduces the moment that you can apply to the girder based on the unbraced length of the girder. And so it's a bigger issue with plate girders. These pictures are from that Colorado bridge that I talked about earlier that collapsed during construction because of inadequate bracing, and the girder wasn't stable. You can see that the consequences are very severe when stability is, when your stability moment is less than your moment capacity. This is not a yield type failure. This is something that happens fairly quickly. And I'll get into that. This is the formula. Nobody should be intimidated by the formula. There's probably a couple of guys out there that know this by heart, and good for you. A couple of things I'll point out is it involves pi. Anytime you see pi in a formula for a beam design or a column design, it implies that there's some kind of Euler buckling happening, and Euler buckling always means failure happens fast. It's not a yielding failure. If you have a beam and bending and you exceed the yield moment, yes, it'll bend. You can see it happen. It probably won't completely fail. If you exceed the buckling moment, it fails quickly. Some other terms in here, there's J, there's G. Every time I see those in any kind of formula, it means I got to do all these calculations and figure out stuff, and it can be a source of error. What's important, what's missing from this formula is Fy, the strength of steel, and that becomes important in some things that I'll go over in a minute. But this formula seems kind of complicated. It is kind of complicated. There's in the very last term, that CW term, I'll talk about that a little bit. That's a warping constant, or it's not a warping constant. It's a factor to apply to your lateral torsional buckling for moment gradient, if you remember that. I'll talk about that in a few minutes. But that can be very complicated. So this is a complicated formula, and it's more complicated than we really need. So there's some good ways to check girder stability. For designers out there, the number one easy way is L over BF is less than or equal to 85. That's just the length of your girder divided by, or the length of your girder in inches divided by the width of your smallest flange in inches. And if it's less than or equal to 85, your girder is 9 times out of 10 stable. You don't have to worry about it. I'll talk about that in a minute. The other way for contractors out there, I think some of the best ways to check for stability before you erect are, one, ask Clark. Clark builds a lot of their girders. He's moving them in and out of his shop. He's flipping them over, putting stiffeners in them, drilling bolt holes, etc. If there's a stability issue, Clark's the first guy to know about it. And if he hasn't called you to tell you that, or called you as the engineer to tell you that, call him if you're concerned at all, and he'll be able to tell you what's going on in his shop and what he's experienced. And then the other way is to ask your steel erector, like Chad. I've worked with Chad for a number of years now, and if Chad calls me up and says he's worried, he's got a good reason to be worried. He's just got that experience moving girders, lifting girders, setting girders, that if there's a problem, he'll let me know, and then we'll dive into some details and do some more detailed calculations and figure out what can be done. I will say that if you exceed L over B, if you're greater than 85 in your L over B ratio, it's not that you can't erect that girder. It's not that you shouldn't design a girder that way. It's just that there needs to be some instructions or some things to be put on the plans or communicated to Clark or the contractor that, hey, you may have to do something special here. As I put this slide in kind of late. The AASHTO and the AASHTO commentary, it actually references this paper. I put the reference on the bottom here, and I don't expect you to read it. But some people went through and they decided they were going to take that L over B of 85 ratio and they were going to test it, and they used all the new LRFD formulas and upgrade it, because that L over BF less than 85 has been around since early 1900s. It's kind of it used to be in the steel manual. But they applied the LRFD formulas to it, and they came up with these other recommendations that if your L over B is less than 60, you're stable. Between 60 and 80, you should do some more calculations, and if you're over 80, you need temporary shoring. Well, that's not true. What they did was they applied the load factor for LRFD basically to those torsional formulas, but if you looked at the torsional formula, I said FY is not in there. So you went to LRFD design, you applied a load factor, but it doesn't, on the back end, you get no benefit, because instead of using just a small reduction factor on your FY's got nothing to do with it. So they've essentially increased their load by 25%, but they haven't affected any other portions of the formula. If you took 85 and divide by 1.25 your dead load, it's like 63. So L over B less than equal to 63 and you're stable. That's what their paper says. They did a lot of research to come up with that. It seemed like it was kind of a waste of time. And then the 1/2 limits for cantilevers is actually complete the opposite. The limit for cantilevers is more like double the limit for a simple span. And that has a lot to do with that CW factor, the moment gradient factor that I pointed out in the formula. And it also has to do with if you have a cantilever, your bottom flange in compression, and typically steel girder design were composite, and in a composite girder, your top flange is smaller than your bottom flange. So now all of a sudden you're looking at buckling with your bottom flange. Your bottom flange is bigger, so you have more strength in your girder. So even though this is an AASHTO, it's in the commentary in the back. I think L over B less than or equal to 85 is really the basic rule of thumb that we should be running with. Steel girder erection. The things you have to look at is the L over BF is typically the entire length of the girder, the entire length of the girder section, not necessarily the length between your pick points or between your pick points. Let's leave it at that. When you pick up a girder, it's most stable if you're at the quarter points in from the end. And there's a lot of contractors out there, that's their policy, always pick a girder quarter points from the end, and that always works, and it's safe. It's actually a pretty good policy. It's not necessarily a realistic policy if you're over a river, if you're over the railroad tracks, if you're in a situation where you simply can't pick up at the quarter points because you can't put your crane there, that's an issue. And sometimes it's just not efficient because you'd have to have 2 cranes, and it's a lot easier to lift with 1 crane if you have the capability. So 0.25L from the ends, it's a good rule of thumb, but not necessary. You do always have to look at the support locations at release. So it's not just about lifting, it's about when you first set that girder down. And I'll go through an example here where we had a girder that was shipped out in 2 pieces. Each piece met the L/B was less than 85, so each piece was stable, but we spliced it on the ground and we went to lift it up over the railroad tracks, and when we went to set it down, it was an issue. And here's a picture. It's pretty obvious, really, looking back at it. You can see the cranes are picking it up probably 40 feet from either end. The girder's stable, it's fine, it's no problem. But when we went to set it down on the abutments and release the cranes, we hadn't planned on a hold crane because there was railroad tracks in the middle, so you couldn't really put a hold crane there. And I'm not sure exactly what happened, but I got the call at 6 o'clock on Sunday night asking what we can do about it. And I didn't design the girder, and I didn't even work for RLW at the time, but they called me anyway. So this was the solution. We actually probably woke up the guys at foreshore in the middle of the night and got a shoring tower to put up near the railroad tracks to support that girder to make sure it was stable. But the example really just shows that even though your girder can be stable during lifting, you always have to check both the lift condition and when you set it down condition, because the setting down condition is more likely to control. I lost my time. Steel girders. All right, so there's a program out there called UT Lift. It's the University of Texas program. It's an Excel-based program, and it's free to download. Like I said, it was written by a guy that works for Baker now. I talked to him last week, actually, about this. It's a great program. It's easy to use. I recommend all designers download it and use it during design. And if you don't do it during design, use it when you check your shop drawings, because it's a great program. You can put all your plate sizes, all your plate transitions. You can put in loads. You can put in additional loads. You can put in point loads. It works for straight girders. It works for curved girders. It's very simple output. It's very simple to use. You don't have to be a structural engineer to use it, actually. You just go through it a few times and with maybe some sample girders that you've lifted before, and you can see how easy it is to read and work. It's capable of analysis with a single crane with a spreader bar. You can analyze the lift with 2 different cranes with 2 different lift points, so you can actually have unequal loads on a crane. So say you have one crane lifting up the girder from the very end and another one's lifting it up 30 feet from the middle. You're not going to have equal loads on the cranes. This program can handle it. It's pretty handy. Like I said, it's easy to use. It's quick, less than 30 minutes to get your results and analyze it and look at it and play with it. You can do your lift points and you can do your support points all very quickly. It's definitely a valuable tool, and I recommend everybody download it and use it. There's one caveat to this. You do need to understand the program. The program uses that CW factor that I talked about earlier, that CW or CB. It's the moment modifier, and it has to do with moment gradient in the beam. And if you guys remember from steel design, you learned about moment gradient, and basically that formula for lateral torsional buckling assumes a constant moment through the girder. Well, you never have a constant moment in the girder. If you have a simple span, you have maximum moment in the middle, and then it goes to 0 at the ends. In steel design, they always told you assume CB is equal to 1 because it's conservative. And that's a good policy. This program, however, uses a CB between 2 and 6, depending on how far you're picking it up from the end of the girder. And I agree with their analysis, and I know how they went through it, and they came up with their CB factors, but the program automatically applies those. And my issue is that nowhere in AASHTO nor AISC do they ever let you use a CB factor greater than 2.3 or 2.5. And so I question the wisdom of a program that's using a CB of 4 or 6 if there's nothing in the code that lets you go above a 2.3 or 2.5. So I think there's some judgment there on the point of the engineer and your familiarity and your comfort using those CB factors. The AASHTO commentary has a bunch of diagrams. It talks about moment gradient. It talks about If you have an inflection point, essentially the moment gradient really comes into effect. If you have an inflection point in your beam, so you go from positive moment to negative moment, that inflection point, it acts as a brace in your girder. So it prevents lateral torsional buckling. So that's what the CB factor is all about. It's pretty complicated. That's actually why I was talking to the designer of the program last week. I was asking him what he felt about that, and he kind of agrees with me. I mean, he was involved with the research at the University of Texas, and their research is solid, and their CB factors that they put in the program, I think, are reliable. Just beware that if something ever went wrong and they called you on it and they said you used a CB factor of 5, how can you do that? Nowhere in the codes is it written greater than 2.3. How can you do that? You need to be pretty comfortable justifying that yourself. But that's kind of a rare situation. The program always uses a CB factor of 2. If you're aware of that and you don't agree with it, you can just take the results of your moment and you can divide by 2, and that's the same as a CB factor of 1. So you can still use UT lift and adjust the CB factor for yourself if you want. Anyway, that's my only comment on the program. As far as UDOT requirements for stability in steel design, in the girder design, the only place where it really mentions checking girder stability, crane lift locations, etc., is in part 5, which is in the checkers, the quality section, and it seems it's a little bit buried. If I had to make a comment to the SDDM, maybe this ought to be moved up into the design section, just because I do think that if the designer's aware of this as he's designing the girder, he can take care of it if it's an issue, or he can put a note on the plan saying that stability may be an issue, maybe some instructions to the contractor or the fabricator. Rather than waiting, I mean, typically the checker doesn't see it until the design's pretty much done. So that's just, but this is what it says. It basically puts responsibility on the checker. It does in the design section, it has some guidelines about your flange width and your flange thickness relative to the length of your girder and the depth of your girder. These percentages here, they pretty much perform the same function as the L over BF ratio that I talked about earlier. It's just a different way of going about it. These are not hard and fast guidelines, they're recommendations. I mean, they're good ideas, this is good design practice, but you don't necessarily have to follow this. So even though it's here, it's good to follow these, but if you don't, I'd fall back on using UT lift really to make sure you're stable. One thing that I think is important is that I think even though stability hasn't traditionally been an issue for steel girders in Utah, it's likely to become more of an issue as we move forward, and these are the reasons why. One is the use of 70 KSI steel. We talked about the lateral torsional buckling doesn't really have anything to do with the strength of the steel, but your dead and live load moment and your girder capacity has a lot to do with the strength of the steel. So if you use 70 KSI steel, you can use smaller flanges. If you use smaller flanges, you might use narrower flanges. So now your BF has gone down, but your length has stayed the same. So now you're going to have stability issues. So that's something to watch out for. The ability to deliver really long sections. Clark, we've delivered 200-foot long steel girder sections. So 220. That's extremely long. I know New York State limits the length of section that you can ship to 80 feet. Pennsylvania, it's 120 feet. So it's pretty easy to check those. I mean, your L over BF is usually not an issue for transport in those states and other states. But when you have a fabricator that's basically right on I-15, and we do a lot of work on I-15, you can ship really long sections. You know, it's worth paying attention to exactly how you're designing your girder. And if you're taking splices out because Clark can ship a 200-foot section, maybe L over BF becomes more of an issue. Design build, of course, the contractor is always pushing the designer to reduce the weight of steel. And if you do reduce the weight of steel, you're likely to make your flanges as small as they possibly can. You won't follow those guidelines in the SDDM, and you'll just end up with a really thin flange. It could cause a stability issue. High-strength concrete decks, as high-strength concrete becomes more, I guess, available and less expensive, the trend may be to rely on the deck and composite steel girders more so than the top flange. And so your top flange, again, just your design could result in a smaller top flange. Again, smaller top flange, but you haven't changed the length of your girder, you could have a stability issue. And then what goes along with the transport is just bigger cranes. a lot of the cranes right now, they're just easier to get bigger and bigger cranes all the time. And there can be situations that would be like you could lift a single crane. You could use a single crane to lift a girder that maybe you used 2 cranes in the past. And if you lift with a single crane and you pick up from the middle and you check UT lift and your formulas, it works great for the lift, but you haven't really paid attention to when you set it down. So you might have a really long section of girder that's only supported at the ends, and you could have a stability issue. So I do think going forward, these issues could start to creep into the design and impact stability. All right, back to UDOT specs. This is just the requirements for steel erection. Calculations for stability are supposed to be provided with the steel erection plan, and I think that's okay. What was it? 2 things: the exceeding the final geometry and some of the member capacities. I think a lot of that really has more to do with when you pour the deck on the steel girders. And most steel design girder programs check that piece of it. They check the dead load with but they assume that the girders are already all set together and they're tied together with diaphragms. The portion of this presentation I'm covering is really that single girder. The diaphragms aren't in yet, and that's the stability I'm concerned about in this presentation. Providing calculations, if you use UT lift, it pretty much checks this box. And that's another reason I recommend using it. It just provides you can put in the actual plate sizes, the actual girder lengths, the actual lift locations, and it provides all the calculations for you. This slide about installation of the steel fasteners, this is just something that I kind of got caught off guard by this summer. Chad called me up. We wanted to splice the wildlife crossing up on I-80. And he said, how many bolts do I need to put in it? And you need 5 because the bolts are really strong. But AASHTO says you need to put in 50% of your bolts in a field splice before you release it from the cranes. UDOT specs exceed that. UDOT specs say you have to put in all the bolts and you have to tighten 50% of them. So I just bring that up because it was something that I wasn't aware of. I just assumed UDOT used the AASHTO spec, but they exceed the AASHTO spec. And maybe Jeremy wants to say something about that later. But anyway, it's a good policy. Just be aware of that for the steel erectors in the room. Back to erection, we talked about the anchoring and the bracing of concrete girders earlier. This section of the UDOT spec covers the steel portion of that. I talked about this earlier. We talked about how the girder may be stable during lift, but when you set it on the supports, it's no longer stable. There's a couple of things we can do about that. One, you could either put a tower up in the middle to brace it. More likely, we're going to use a hold crane. So you'll use another smaller crane to hold the center of the girder to keep it stable while you release it from the girders that have actually performed the lift in the major part of the set. It's pretty common practice. I have a slide later that shows this. The UT lift program is great. You can analyze this really quickly because the UT lift program, it gives you the actual moment due to dead load in the girder, and of course the dead load is pretty much uniform load. And when you put the hold crane on it, the hold crane is equivalent to a point load in the other direction. So you can actually just figure out the moment you need and the point load you need for the hold crane to offset the dead load moment of the girder to make your girder stable. So like I said, UT lift gives you all those values, and it's a really quick calculation. PL/4 is the moment equation for your hold crane. And then another way to do that is to where you want to put your hold crane, you can kind of take LB and you can say, well, if my unbraced length is cut in half because I'm picking it up in the middle, my L over BF is less than 85, and so it should be stable. And that's kind of a decent rule of thumb, but it's not reliable. Really, if you want to use a hold crane, you should do an analysis using UT lift. All right. So which diaphragms do you put in first? I mean, typically we like to lift girders and girder pairs if we can, because it's typically stable when you have 2 girders. But when you can't, as like Bangor Highway this summer or this spring, we didn't have crane capacity to lift 2 girders in pairs. So we lift 1 girder at a time. We held it with a hold crane. You put up the second girder, and then you have to put in some diaphragms. How many diaphragms do you need to put in? Where should you put those diaphragms in so you can release the crane and go get the next girder to put in? If you just look at it from an unbraced length point of view, you should say, well, we should put in the center diaphragm first because that cuts your length in half. You've reduced your unbraced length, so you should be good. Well, it turns out that's kind of true, but mostly what's better is to provide some end diaphragms first and then maybe put one in the middle. It's because the end diaphragms, or the diaphragms closer to the ends, provide some warping restraint. It's just the way that the lateral torsional buckling works. If you can square it up at the ends, you're essentially creating torsional resistance at the ends, less likely to roll over. This is engineer's judgment. I think my practice is usually to put in maybe 2 diaphragms, every other diaphragm right at the ends of the girders, and then put the center one in. So if you have 9 diaphragms, we'll put in 4 or 5. A note on 2 girder lifts. Most of the time they're stable, but not all the time. The general rule here is that if your girder spacing is less than the height of your girders, even a 2 girder system is probably unstable. The formula to check this is similar to the lateral torsional buckling formula. It's a little bit easier. But the general rule really is just that it's not a problem unless your girder spacing is less than the girder height. Where could this be a problem? It's a problem on maybe pedestrian structures where you have a very narrow deck, you're only 10 or 12 feet wide, and you need 2 or 3 girders. Your girders are likely to be closer together than they are high, so you could have a multi-girder stability issue. You can actually have a stability issue with 3 or 4 girders, not just 2 girders, but usually even if you have 3, you're stable. Another location this occurs is railroad girders, railroad bridges. The railroad loads are usually so high that your flanges are thick and your spans aren't that long, so it's not a stability issue, but they typically are closer together than they are high. Like if you ever designed a railroad bridge, you know that. They're like 1.5 feet apart and they're 3 or 4 feet deep. I'll get some examples now of, this is a 2 girder lift that happened up in Idaho maybe 10 years ago. And the spacing of the girders was less than the girder height. Chad was up there, this was an adventure, and we started to pick it up and the 2 girder system started to roll. We hadn't really anticipated this, it was a big panic. We went down, we had another similar bridge down in Clark's Yard. We all got together one weekend and built a bridge in Clark's Yard and practiced picking it up. The solution there, it ended up being, we actually provided these horizontal trusses in maybe the end 40 feet of these girders. These girders were 250 feet long, or maybe 275. They were pretty long, 250. So this was the solution. We got together and we created this horizontal truss at the ends of the girders so we could lift in girders in pairs and it would be stable. And one of the points I want to make here is even if you exceed the L/BF ratio, if there's a girder stability problem that you find in UT lift, there are things you can do about it to still make it constructible. Maybe not preferred, but there are things you can do. This is the typical chain down of a steel girder. If we're going to erect steel girders before we have the other girders up, you just chain it down similar to the concrete girder. Here's an example. This is a 2 girder lift. It's a railroad bridge. You can see that they're closer together than they are high. But again, the spans were fairly short, and it's just erecting girders in pairs. This is a typical beam clamp that we pick up the girders with. You can see the clamp goes around the top flange and hopefully picks up the girder very close to the center of the web. This is pretty typical. This is a RLW custom design. There's plenty of commercial products out there. The big red bar is the spreader bar. A note on when you pick up a girder like this with a girder clamp, I've never come across a situation where the connection between the web and the flange has been even close to the capacity of the girder. So it's always strong enough. It's not something you really need to check. There are provisions in AASHTO if you need to check this or you feel you need to check this. You can actually spread the load or where you're picking it up from on that clamp. It's the width of the clamp plus like 12 inches in either direction. So you end up with a lot of weld, and the strength of that weld compared to the weight of the girder is typically not an issue. The thing to make sure is that you are picking it up close to the web. You don't want to be picking up the girder at the ends of the flanges because you could bend the flanges or warp the flanges. Here's an example. What I want to show in this picture is we have this is the Bangor Highway Bridge. You can see on the right we have a large crane with a spreader bar picking up the longer section of girder. On the left, this is a smaller section of girder. It's just a single clamp, a single point pick for the crane, so there's no spreader bar or anything. Spreader bars are good because if you don't pick up the center of gravity exactly, it kind of distributes the load to your crane, makes the girder easier to handle. But Chad's kind of a big fan of the single girder, the single point pick, and I am too. I think it's a pretty slick way to do things. Your girder is stable, and it only takes one crane. It's pretty quick. Lifting with overhang brackets on is typically fine. This is an example of us doing it with a concrete girder. The actual cover page of the UT Lift program shows lifting a curved steel girder with half the diaphragms already bolted to the girder. So you can imagine that this puts some eccentric load on the girder, and it could cause it to roll. It could cause some lateral torsional buckling problems. But again, if you run UT Lift, it gives you the option to put in additional loads, so you can always put in additional loads and check to see if you think that might be a problem or not. Chad's not a big fan of lifting with eccentric loads on it, so you always talk to the crane operator. This picture is just kind of a neat picture of something we do. This is an air splice. One girder set. The second girder is being flown in. This is just over some water and how our crews go about making that splice when you don't have access from down below. This picture is just to demonstrate the hold crane. In the picture, it's hard to see. There's a smaller yellow crane out there, and it's in the middle of the girder, and it's just holding up the center of that girder. We've already released the crane left of the picture, and Chad's still hooked up with the spreader bar with the big crane, but he's about to let that go. So this allows us to put the single girder up there, use the hold crane. The hold crane's probably only holding 50,000 pounds, keeps the girder stable, allows Chad to go pick the next girder, lift it, put it together, and then put the diaphragms in to create a stable structure. So really, that's kind of the presentation. I think the key takeaways of this presentation are that normally girders are pretty stable for what we do here in Utah. Checking L over BF to make sure it's less than or equal to 85 is just a good check I think everybody should do throughout this entire life cycle of a project, from designer through erector, just to make sure that we're safe or in the ballpark anyway, within the rule of thumb. I think understanding the difference between a lift condition and a set condition is important. I think the problems, we've only had 2 or 3 problems in the last 10 or 15 years that I know about, but I think a lot of them really had to do with not really paying attention to the set condition. They're fine during lifting, but when we go to set, we have some problems. And then using that UT Lift program, especially for all the designers in the room, if you're designing, just download that program. It's free, it's easy to use, and it gives you a lot of information. You can do a lot with it. So that concludes what I wanted to go through. I want to kind of open it up. I think Clark had some things to say about some curve girder specs maybe. And any comments Jeremy or Chad have?
In addition to what Jim's been discussing as far as girder stability, I'd like to talk a moment, with Jim's permission, about the vertical nature of webs during construction and during the life cycle of the structure. For many years, this just wasn't a concern. Most of the bridges were straight, the skews weren't extreme, and the load on the girders as they were being constructed was equal. There was not differential deflection from one girder line to the next. Now, particularly in the last 20 years, as we have more skews, longer spans, higher strength steel, and tighter curvature, horizontal curvature, it has become a real concern when designers specify that the girder web be vertical after full dead load. I think there's an assumption with designers that that's always been the case. It just seems right to a designer and really to an erector as well. The first thing an erector will do, as Chad will tell you, a lot of times they'll put a plumb bob or a level and make sure those girders are vertical as they're being erected. The problem with that in the modern era is that as the bridges have become more complicated, it is very difficult to erect a bridge that has differential deflection and maintain the webs of those girders vertical after full dead load. And in trying to do so, it can actually make the bridge unconstructable because to have a web vertical after full dead load means that we need to detail that structure so that we warp the girders opposite the way they're going to rotate during construction and actually force fit our diaphragms to make the girders lean over the opposite way so that when we apply dead load, girder dead load and concrete dead load, we bring the webs back vertical. NSBA has come out with a document. They worked on it for about 4 years, finally published it in 2016, that gives designers examples of how to mitigate the risk of designing a bridge that's essentially not constructible or unsafe to construct. And as Chad will tell you, there's nothing worse than being on a tight window. You're erecting at night, 6-hour window. You've got to release your traffic first thing in the morning. And if you can't make the connections between your diaphragms, between a pair of girders to stabilize that so you can let go of the girders, it's just an impossible task. And so I would strongly recommend this document. But what in essence it does, it tells you in certain conditions, depending on skew, depending on girder horizontal curvature, that you do not want the webs vertical after full dead load. You may want them, or be able to live with the fact that they are not going to be vertical. They're going to be rotated. I brought about 25 copies, but this is easily downloaded, free of course, at nsba.org or aisc.org. It's called Steel Eye Girder Bridge Fit. And I would strongly recommend it. We're using it all the time now. And it's almost mandatory for us to use it as we begin detailing, because the geometry of the bridge is set during shop drawing detailing. And the last thing we want to do is detail it one way and then have the designer review our shop drawings and say, that isn't the way I wanted it. So this is a great document as you're designing to use.
Does anybody have any questions? Comments? Anybody want to tell me I'm wrong? I'm okay. I'm always afraid to give these presentations because I'm always afraid there's like some high school sophomore out there that knows more about it than me. Okay, that's it. Thanks.